Now that we're familiar with radicals and roots, I'd like to take some time in this lesson to talk about solving algebra equations which involve radicals. But before I do that, I'd like to introduce a very important idea, and that's rational exponents. So here's what I mean. When we're talking about polynomials, we saw terms like 4x to the fifth, or negative 7 times x cubed, and maybe 123 times x. The key fact about these terms in a polynomial is that all of the exponents on the variable x need to be positive integers. So, for example, something like 7x raised to the 1/2 power is never a term in a polynomial. Okay, so maybe 7x to the 1/2 would still be useful to us somehow, even if it doesn't get to be in a polynomial. Well, in fact, it is very important to us because 7 times x to the 1/2 is exactly the same as 7 times square root of x. And here is a connection then to radicals. We can always rewrite a radical symbol like the mth root of x as x raised to the 1/m power. And although something like this is not a polynomial term, at least if m is not 1, it's still extremely important in algebra. In fact, lots of the usual rules about exponents still apply when you're working with fractional exponents, or what are often called rational exponents, because the exponent is the ratio of two whole numbers. So let me just remind you very quickly of the laws of exponents that we have in algebra. So assume m and n are two rational numbers. So they might even be whole numbers, since whole numbers are fractions with denominator 1. Then, as long as we aren't causing any division by 0, we have the following rules. First, if you take a to the m times a to the n, it's the same as a raised to the m plus n. Secondly, if you have something like a to the m and you raise that to the nth power, then it's the same as raising a to the m times n. Also, if you have a product like ab raised to the m, it's the same as a to the m times b to the m. And a to the negative m power is the same as 1 over a to the positive m power. If you have a ratio like a to the m divided by a to the n, then it's the same as a to the m minus n. And lastly, if you have a fraction like a over b, all raised to the mth power, then that's the same as a to the m divided by b to the m. Now, we've already used some of these laws in earlier lessons. In fact, you've seen, for example, something like 50 raised to the 1/2 equals 25 to the 1/2 power times 2 to the 1/2 power. That uses one of the rules we just talked about. And then that can be simplified a bit because 25 to the 1/2 is the same as square root of 25, which is 5. So in fact, that all simplifies as 5 times square root of 2, because 2 to the 1/2 is square root of 2. Now, let's look at another example or two of how these laws can be very, very helpful to us as we try to simplify some of these terms that have rational exponents. Let's see if you can do this one. Simplify negative 4 raised to the 1/3 power times negative 4 raised to the 2/3 power. Now, the way not to do that problem is to try to figure out what negative 4 to the 1/3 is by itself and negative 4 to the 2/3 is by itself. Neither of those numbers is clean or friendly. Now, they do exist as real numbers, so they're well defined, but neither one of them is really going to look very nice by themselves. So let's see if there's a law of exponents that we talked about earlier that can help us to clean up this problem. Well, the first law that I shared with you said that a to the m times a to the n equals a to the m plus n. So in this example, if I let a equal -4 and m equal 1/3 and n equal 2/3, then I will have -4 to the 1/3 times -4 to the 2/3 equals -4 to the sum 1/3 plus 2/3. But 1/3 plus 2/3 is equal to 1. So this thing simplifies as -4 to the 1, which is just -4. So see, that wasn't so bad. Once we use the laws of exponents to put the two pieces together, even though neither piece by itself was very clean, we saw that the product was just equal to -4. Let's now look at one more of this kind of problem. I think it's actually one of the most important examples that you can see when it comes to simplifying terms that have rational exponents. And again, this is going to use some of the laws of exponents that we just discussed. Here's the example. I want you to simplify 81 raised to the 3/4 power. Okay, first things first. Notice that I can rewrite 3/4 as 3 times 1/4. That's important because I want to use these laws of exponents. And thanks to those laws of exponents, I can now say that a to the m raised to the n is equal to a to the m times n. So this problem of finding 81 to the 3/4 actually allows me two different plans of attack. I can let m equal 3 and let n equal 1/4, and then I can rewrite the original problem in two very different ways. 81 to the 3/4 is equal to 81 cubed, all raised to the 1/4, and it's also equal to 81 raised to the 1/4, all cubed. Both of those are exactly equal to the original problem, and they're both perfectly legitimate. I want to stress that. But I think one of them is smarter than the other in terms of attacking the problem. I would ask you first, which one would you pick? Well, I often see students pick the first choice, which is 81 cubed raised to the 1/4. And if you really want to know the truth, I think part of the reason that some students choose that option is that they're more comfortable raising a number to a power like 3 than to a power like 1/4. So they're sort of putting off the raising to the 1/4 until the end, like some kids saving their vegetables to the last part of a meal because they really don't want them. They're just trying to put it off. Believe it or not, even though that way of doing the problem is perfectly good, it's actually not the best way. And here's why not. If you try to raise 81 to the 3rd power first, 81 raised to the 3, you're going to get a very large number. In fact, what you're going to get is 531,441. Now, try finding the 4th root of that. I wish you a lot of luck. It's going to take a long time. So by computing the power of 3 first and then the 1/4 power, the problem gets very large, and then at the end it gets smaller when you do the 1/4 power. Well, here's my question. Why not do things in the opposite order? Let me show you how. You rewrite the 81 to the 3/4 as 81 to the 1/4, all raised to the 3, all raised to the 3rd power. Okay? Now by doing that, the 81 to the 1/4 is actually going to get small. In fact, do you know what 81 to the 1/4 is? It's just 3, because 81 to the 1/4 is the same as asking, what number can I multiply by itself 4 times to get 81? 3 times 3 times 3 times 3 is 81. So the original problem is the same as 81 to the 1/4 to the 3rd power, but what's inside those parentheses is just a 3, and that means you're just looking at 3 to the 3rd power, which is 27. The final answer is 27. And do you see how doing the 1/4 power first actually made the problem get smaller, and then the cubing, or raising something to the power of 3, was easy? It's much better than trying to find the 4th root of 531,441. You should seriously keep this example in mind for future. I promise I see students do these kinds of powers of taking or simplifying powers with rational exponents, and they're constantly blowing up the problem to something very large and then trying to make it small at the end. You really want to do the work in the order I showed you, and believe it or not, this kind of problem can even show up in a pre-calculus or calculus class. So you want to keep this kind of example in mind for the future. Okay, I've said enough about rational exponents for this lesson in terms of just simplifying. Now what I want to do is talk about solving equations that involve rational powers and radical symbols. So before we jump to the examples, I need to mention a very important fact that we're going to use a few times in the examples. Here's that fact. Whenever x as a variable is greater than or equal to 0, in other words, when it's equal to 0 or positive, if you have the square root of x and you square that, then that's equal to x, okay? Now, that fact is not true when x is less than 0 because the square root of x doesn't make any sense when x is less than 0 or when x is negative. I'm going to use this fact a lot in the examples that are going to come up in just a moment. So, again, remember, when x is greater than or equal to 0, the square root of x squared equals x. Okay, let's get started with a very straightforward example just to illustrate the idea behind how we're going to solve these kinds of equations. Let me suggest you try it first just to see how it goes for you, and then we'll do it together. Solve the equation square root of x minus 7 equals 2. Now, the first thing you're going to want to do in this example, as with most of the examples we're going to see in this lesson, is you want to do something I call isolating the radical. And what that means is you're going to want to try to get the square root symbol by itself on one side of the equation. It doesn't matter if it's on the left side or the right side, but you want to get the radical by itself. You want to isolate the radical. In this case, we're going to isolate that radical by adding 7 to both sides of the equation. The left-hand side will then just become square root of x, and the right-hand side becomes 9 because 2 plus 7 is 9. So now you're down to the equation square root of x equals 9. If we now square both sides of this equation and use that important fact that I mentioned at the beginning of the lesson, then we'll have x equals 9 squared. Square root of x squared is going to equal x, and 9 squared is going to be the right-hand side, which is 81. So our answer, our solution to the equation is x equals 81. Now it's going to be very important, and I can't emphasize very important enough in this sentence, it will be very important in this lesson that we check our answers. So even though it was pretty easy to check this answer, then it will be easy in just a moment, it's only going to take a couple steps, we're going to do it anyway, because in later examples we're going to find that some of the numbers that we think are solutions are really imposters. So let's do that here. Let's check our answer by plugging it into the original equation and seeing if it really is a solution. Our original equation was square root of x minus 7 equals 2. We think x equals 81 is a solution. We plug in 81 and we get square root of 81 minus 7 equals 2. That's the same as 9 minus 7 equals 2, or 2 equals 2. That's a true statement, and therefore 81 really is a solution of the original equation. Now, let's look at another quick example of solving a radical equation. And again, I'm going to suggest you try this one on your own first, and then we'll see how you did. Solve for the variable t in the equation square root of t minus 2 equals 5. Now notice in this problem that the square root is already isolated. It's already by itself on the left-hand side. And so really there's actually nothing more to do than just to square both sides of this equation. Now before I do that though, I want to point out that there's more under the radical symbol than just a t. There's actually a t minus 2. Now, is having that extra minus 2 under that radical symbol a problem? Absolutely not. We're just going to proceed like we did in the previous example by taking the original equation. Since the radical is already isolated, we're just going to take that equation and square both sides of it. And when we do that, and we use that important fact that I mentioned a few minutes ago, we're going to have square root of t minus 2, whole thing squared, equals 5 squared. And that means that we just have t minus 2 on the left equals 25 on the right. And now if you add 2 to both sides, you'll just have t equals 27. Now our final answer is 27 here. Again, we have to check to make sure that that really is a solution. So I plug 27 back in for t in the original equation, and I have square root of 27 minus 2 equals 5, which is the same as square root of 25 equals 5, or 5 equals 5. Thumbs up. That really was a solution, so 27 is my final answer. Now, I want you to notice one other quick thing about this example before we move on. Let's just talk about this briefly together. I'm sort of trying to walk you down an incorrect path, if you will, but just stay with me. Someone might say, okay, the original equation was square root of t minus 2 equals 5. Why isn't t equals negative 23 a solution? After all, if you plug in t equals negative 23, you'll have under the radical sign negative 23 minus 2, which is negative 25, and the square root of 25 is 5. So why isn't t equals negative 23 a solution? Well, because it would be saying that the square root of negative 25 equals 5. I was trying to hide that negative from you there for a second. But the square root of negative 25 makes no sense as a real number. So you can't hide those negatives. You've got to watch them, and you have to be very careful. You'll never be able to find a real number that you can multiply with itself to get negative 25. So t equals negative 23 is definitely not a solution of the original equation. We found that one solution, t equals 27, and that was the only solution of that equation, and that finishes that example. Okay, let's look at another example now. The example will be this. Solve the following equation. The third root of x plus 3 equals the third root of 5x minus 9. Now, this is an interesting kind of equation, actually. In the earlier comments, I said you wanted to isolate the radical, get the radical by itself. Unfortunately, there are actually two radical symbols here. How in the world are you going to get the radical by itself if there's one on each side? It turns out that you don't have to worry about it in this kind of an example, because what you don't want to do is actually put two radical symbols on the same side of an equation if you don't have to. In fact, you really don't have to do anything with this original equation other than just raising both sides by the power of 3. So leave the equation as it is and just raise both sides to the power 3 and then solve the equation. So I'm going to suggest you try that now, and let's see how you do. Okay, we started with third root of x plus 3 equals third root of 5x minus 9. And I raised both sides to the power of 3. And using a rule similar to what we discussed earlier, basically, you're just going to have x plus 3 to the 1/3 cubed equals 5x minus 9 to the 1/3 cubed. And the 1/3 will multiply with the 3 thanks to the laws of exponents. That's just 1. And so you really only have x plus 3 to the 1 equals 5x minus 9 to the 1, or x plus 3 equals 5x minus 9. This is a linear equation. You know how to solve this now, so let's just walk through it just to finish. If you subtract the x from both sides, you'll then end up with 3 equals 4x minus 9. And if you then add a 9 to both sides, what you'll really end up with is 12 equals 4x, and dividing both sides by 4 is going to give you x equals 3. So I believe that my solution is x equals 3. Now what I'd like to do is check that solution. And you have to do this. It's very important that you check all of these kinds of things with these equations with radicals. So you plug in a 3 for x in the original equation, and you get the following. Third root of 3 plus 3 equals third root of 5 times 3 minus 9. The left-hand side is just third root of 6. That's no problem. The right-hand side is the third root of 15 minus 9, which is also third root of 6. So what you have is third root of 6 equals third root of 6. Well, that's a true statement, and therefore you know that x equals 3 was really a solution of the original equation. Now, By the way, I have no clue what the third root of 6 equals, but that's not the problem. All I know was third root of 6 equals third root of 6. That's a true statement. So even without knowing what the third root of 6 really equals, I know it equals itself, and so I know that that equation was true, and therefore x equals 3 really checks out. Now, I'd like us to try another one of these equations, try to solve another one of these equations just for the practice. Let me give it to you first, see how you do, and then we'll come together. Solve 3x equals 2x plus the square root of 4x plus 5. Now, here, as we get started, you really do have to isolate the radical. And the way you're going to do that is subtract the 2x from both sides of the equation. And when you do that, the left-hand side becomes 3x minus 2x, which is just x. So now we're down to x equals square root of 4x plus 5. You've isolated the radical. Now what do? We square both sides of the equation, or raise both sides to the second power. And when you do that, the left-hand side is x squared, and the right-hand side is just 4x plus 5, thanks to the fact that we talked about earlier. Now you're just looking at a quadratic equation. We know how to solve that, so let's do so. X squared equals 4x plus 5 is the same as x squared minus 4x minus 5 equals 0. And guess what? That factors. It factors as x minus 5 times x plus 1 equals 0. If you split that up now into two smaller equations, it's the same as saying x minus 5 equals 0 or x plus 1 equals 0. And that's the same as saying x is 5 or x is negative 1. So our solutions to the original equation appear to be x equals 5 and x equals negative 1. But as I've been saying, we've got to check to make sure that both of these really are solutions. So I'm going to go back to the original equation, and I'm going to plug in 5, and I'm going to see if it really does solve it, and I'm going to plug in the negative 1, and I'm going to check to see if that's a solution as well. The original equation was 3x equals 2x plus the square root of 4x plus 5. Plugging in a 5 all the way through wherever I see an x, I'm going to have 3 times 5 equals 2 times 5 plus the square root of 4 times 5 plus 5. And that simplifies to 15 equals 10 plus the square root of 25, or 15 equals 10 plus 5, 15 equals 15. That's correct. And that means that we've confirmed that x equals 5 really is a solution. Now, let's check the x equals negative 1. Plugging negative 1 into the original equation, I have 3 times negative 1 equals 2 times negative 1 plus square root of 4 times negative 1 plus 5. And that's the same as negative 3 equals negative 2 plus the square root of negative 4 plus 5, or negative 3 equals negative 2 plus the square root of 1. And that's just 1. So I have negative 3 equals negative 2 plus 1. Oh, be careful. The right-hand side then simplifies to just negative 1. So we have negative 3 equals negative 1. That's a false statement. So what do? Well, I guess you could go check your arithmetic to make sure we didn't make a mistake, but we didn't. It means by coming up with a false statement at the end that x equals negative 1 isn't a solution of the original equation. In such cases, we would refer to this number, x equals negative 1, as an extraneous solution. It's what I like to call an imposter solution. Bottom line, it's not a solution of the original equation. It might be a solution of an equation that we got as we were working through the steps, but it's not a solution of the original equation. And if you're not a solution of that original equation, you're called an extraneous solution. So we throw the negative 1 away because it's not a solution of the original problem, and we keep the x equals 5. And x equals 5 is the only solution of that equation. Now, let's try another example of this very kind of thing, and let's be really careful about whether we have real solutions or not. Try this one yourself, but be careful and check your answer. Solve 8 plus the square root of 4y equals 4. Okay, what's the first step? Well, isolating the radical. You got to get the radical by itself. To do that, you're going to subtract the 8 from both sides, and you'll have square root of 4y equals 4 minus 8, which is square root of 4y equals negative 4. Now, what have I been doing in all the other problems? Squaring both sides. And when I do that, and I use that important fact we talked about before, we're going to just have square root of 4y squared equals negative 4 squared. And that's just going to simplify to 4y equals 16. I can divide both sides by 4, and we'll be done. We'll have y equals 4. Now, if we were foolish or in a real hurry, we would just stop and circle y equals 4 on our page, and we'd move on. But that would not be a wise choice. We should think of y equals 4 as a candidate or a possible solution for the original equation. The only way to know for sure whether y equals 4 is a solution is to plug it back into the original equation and see if we get a true statement. So let's do that. Go back to 8 plus square root of 4y equals 4 and plug in 4 for y. Well, you're going to get then 8 plus square root of 4 times 4 equals 4. 8 plus square root of 16 equals 4. So you're saying that 8 plus 4 equals 4, which says 12 equals 4. And that's not true at all. That's a false statement. What does that mean? It means that y equals 4 is one of these extraneous solutions, which means it's not really a solution of the original problem. It might be a solution of something later, but not of the original. And that means that we actually have no solutions of the original equation. Is that a problem? No. It just means that what we were given in the first place actually has no solutions. Okay, I'd like to try another example now, which is a bit more complicated because of what is under the radical symbol, but it's actually not that bad. If you can solve this one, you've probably mastered just about everything from today's lesson. So here it is. Solve for the variable x in the equation 4th root of x to the 4th plus 8x squared minus 32 equals x. Now, what's our first step in these kinds of problems? Isolating the radical. But that's already been done for us. Notice that the left-hand side has this one big radical symbol in it, nothing else, and the right-hand side has whatever it has. It has an x. But the point is, the radical has already been isolated. So what's the next step? Well, we need to raise both sides of the equation to a good power to sort of get rid of that radical. And in this case, since we're looking at a 4th root, we're going to raise both sides of the equation to the power 4. And when I do that, the left-hand side becomes x to the 4th plus 8x squared minus 32, all raised to the 1/4, then raised to the 4th power. And the right-hand side is just x raised to the 4th power. So I've raised both sides to the 4th power. And thanks to the laws of exponents, that 1/4 and the 4 on the left-hand side are going to multiply together to give me a 1. So that the left-hand side is just x to the 4th plus 8x squared minus 32 raised to the 1. And I can just write that as x to the 4th plus 8x squared minus 32. And the right-hand side is just x to the 4th. Now, when I subtract x to the 4th from both sides, look what happens. I end up with just 8x squared minus 32 equals 0. And now, what looked a bit messy at first, and probably a bit fearful for some of us, is now very straightforward to solve. This is just a quadratic, and we know how to attack those. So let's finish this problem by factoring this quadratic and seeing what the solutions are. You have 8x squared minus 32 equals 0. Factoring out an 8 that's in common on the left-hand side gives me 8 times the quantity, x squared minus 4 equals 0. Dividing the 8 over to the other side just gives me x squared minus 4 equals 0, because 0 divided by 8 is still 0. And now I can factor x squared minus 4. It's x minus 2 times x plus 2, and that's equal to 0. And setting each of those two pieces equal to 0 then tells me that my possible solutions are x equals 2 and x equals negative 2. I say we check them both. Plugging in x equals 2 to the original equation is going to give me 4th root of 2 to the 4th plus 8 times 2 squared minus 32 equals 2, which will simplify to 4th root of 16 equals 2, and that's just 2 equals 2. So I know that x equals 2 is really a solution. Now, let's check x equals negative 2. But I want you to think about this for a second. Let's just do this intelligently for just a moment. If you plug in x equals negative 2 into the original equation, you'll have the fourth root of some quantity equals negative 2. In fact, what you'll have is fourth root of 16 equals negative 2. And the key word there is negative. When can the fourth root of any number equal a negative 2? In fact, the fourth root of 16 is positive 2. So this equation actually is false, right? That square root or fourth root of 16 is equal to negative 2. That's a false statement because it's really saying that 2 equals negative 2. And therefore, x equals negative 2, which we tried plugging in, is not a solution. It's actually one of these extraneous solutions. And so I know that the original equation only has one solution, and that was x equals positive 2. Now, in this lesson, we've talked extensively about how to solve equations which involve radicals or fractional powers. Next time, we'll talk about the graphs of some of these functions that involve radicals or root functions.